Good afternoon, all. I'm going to cover the thermal management aspects using Ansys tools. So first, we'll first go through why thermal management is needed, what are different types of cooling, what is the workflow for thermal management in Icepak, uh, special capabilities of Icepak like Optimetrics, automation, multiphysics, and then we will summarize. So as we can see, right, we can see electronics everywhere in engine management systems, autonomous controls, infotainment and control systems, passive safety systems. So everywhere there is electronics, and as there is electronics, there is a need for thermal management. So why do we need thermal management here? So these chips are quite small, but they do have some power dissipation as heat. And what we see here is that more than 50% of electronic failures are related to temperature or thermal management. So, and in addition to that, the junction temperature of the ICs, as they increase, the rate of failure exponentially increases. That is the reason why we need to worry about the temperatures, and we need to manage the thermal aspects of the electronic devices. So where does this heat come from? So we have a lot of electronics embedded everywhere, and then that electronics is going to consume certain voltage and current, perform its electronic function. And in addition to that, it is going to dissipate some part of that energy which is consumed from the electrical side into heat. So that heat is going to, if it is not managed well, it is going to increase the temperatures, and as a result of that, it can have two impacts. One is, if it crosses the limit line of the operating temperature ranges, it is going to fail the device, so it will not function. That is one consequence. Second consequence is it may degrade the performance. So if you expect something to operate at certain speed, it may operate at a slower speed, so it's kind of derating. So it will either damage or derate if we do not manage the heat dissipated within electronic devices. Now, how much heat does these devices generate? So now it depends on different types of devices. I'll cover some of them, like passive devices, for example, the traces on the PCB. As the current goes through it, it has I square R loss associated with it. There are resistors again, inductors, capacitors. So these are all passive devices which will dissipate heat in form of, mostly in form of I square R, in proportion to the current passing through it and the resistance they offer. There are active semiconductor devices, for example, ICs, antennas, and all. So they have certain non-linear components of resistances as well as switching losses. So that the information about the losses generated by these devices will be mostly in the component data sheets, where they will either specify the efficiencies or the on resistances of those devices, and based on that we can compute the losses. Third part is electromagnetic devices, where we might have motors, generators, transformers, radars, wireless communication systems. So these devices, right, we can simulate using ANSYS tools and then get the loss information in those devices calculated by ANSYS tools and then transfer it for thermal simulations. So that is the electromagnetics part. So as you see, there are different components in the electronic system, and each of them we need to worry about what is the loss associated with it, not the rating, but the loss, what is being lost as heat. And then that heat we need to manage. So where does this heat go? Now, either the component and the systems are sitting on PCB and in some enclosure, so it goes to air, or it gets conducted through the board and then radiated to the air. Or if we are using active cooling systems, for example, a cold plate where liquid is being circulated inside that plate, then it goes to the coolant. So we need to define these different heat dissipation pathways so that we do not exceed the stipulated limits of temperatures. And as I said, it is going to impact in two ways. Either it will totally fail the system or it will derate the system. So that's where the thermal management is important. Now let's look at what are the different types of cooling systems. So there are like active cooling systems where we are placing a fan and forcing air over the system, or we are using a cold plate where we are forcing a liquid through the cold plate, and all the electronic devices are sitting on that plate, which is being maintained at certain temperature by the forced cooling of the liquid. Or there are like photovoltaic thermal systems. When it comes to passive cooling, we have a natural convection cooling where there is no fan. It's just based on the temperature gradients in the air surrounding it, which drives the circulation of the fluid, and then it drives the heat transfer. Or everything is maybe immersion cooling is now a coming technology for servers and all, where the all electronics is embedded in non-conductive liquid, and then that liquid drives the natural convection currents based on the temperatures and keeps the system cool. So that's kind of a natural water cooling highlighted here. There can be heat pipes, so which are typically used in laptops, where it makes use of phase change, liquid to vapor phase change. It uses a latent heat to absorb more amount of heat in a shorter space, and then finally it dissipates it to the air. The next type is the phase change material. So typically this phase change material talks about solid to liquid kind of a phase change. It is basically used as an absorber. So maybe for the system which works at high dissipation only for certain amount of time, that is where these phase change materials are used. Or we can use phase change materials with additive cooling, where we can use nanoparticles or advanced mechanisms to increase the surface area exposed, for example fins or porous metal, to cool the systems well. So these are different types of techniques. We can simulate most of them in Icepak uh, using the Ansys tools. Now, let me come to the applications where Icepak is used for predicting the temperatures. So if we see on the semiconductor side, it is used for wafer coating, underfill, reflow analysis. On the aerospace and defense, auto electronics, it is used for control panels, IGBTs, LEDs. Industrial and power electronics, it is used for bus bars, servers, solenoids. On the networking side, it can be used for data centers, antennas, towers, format boxes, and also in the consumer goods like smartphones, uh, desktops, LCDs. So there are a range of applications where iSpec can be used from package level to the server room level. So it can handle a lot of length scales easily. Now let us talk about the workflow. So for Icepak, the workflow is basically we bring in the geometry, we can bring in the mechanical CAD, which is the support structure, as well as the electronics CAD, which has the board, components, traces in the board. All of that can be brought in. We can solve steady state as well as time transient problems. And it captures all the physics, like we can have we can have a conduction, convection, and radiation. All the modes of heat transfer are captured comprehensively. Uh, then we go for meshing, then we go for solution settings. That is where we select what type of problem we want to solve. Do we want to solve only conduction or conduction plus flow, or only flow? So those kind of selections we can do. What radiation models we want to use, that is something which is selected in the solution part. Then we can do the post processing. We can plot temperatures on cut planes, on surfaces. We can see how the fluid is moving around in the support structure which surrounds the electronics, or how the fluid is moving around the electronics. That can be seen through the vectors with different types of animations. We can create the reports which say that how is the heat balance inside the system, where the temperatures are high, it reports out the highest temperatures for each component and also the system. We can monitor like live while the simulation is going on. We can monitor those temperatures. We can use network models for representing complicated IC systems inside Icepak. We can also evaluate the fan operating points based on the system resistances. So this is the typical workflow for Icepak. Now I'm going to show you one use case where we are evaluating different types of thermal management options. So on the left top side, you can see that there is a system which is natural convection cooled. We are not using any heat sink and the temperatures are 115 degrees centigrade. Then we switch to adding a heat sink on top of the IC package. So it is natural convection with heat sink, and then now the temperatures have gone down to 107 degrees centigrade. And then the last option is basically where we force the air. We not only add the heat sink, but we also force the air. And as a result, we can see the maximum temperature has come down to 59 degrees centigrade. So these are like different types of options that we can evaluate even before building the actual device. So that's the benefit of doing these thermal simulations. We can evaluate different options and select based on the available resources and the constraints that we have. Another example of Icepak using Optimetrics, that here we can optimize the placement of the fan. So what you see in these pictures, which is moving on this plane, these two red dots represent the fan, and then we can see the velocity vectors as well as the temperatures because of the movement of the fan, and then decide where the fan should be kept to efficiently cool the system. So we can use this design of experiments to create a response surface, and then using the response surface we can easily do the optimization and then later verify the optimized design. So these kind of capabilities we can utilize in Icepak for not only for different kind of case studies as well as optimization. Another advantage of Icepak is on the scripting side. So it has Python-based scripting. We can record the operations that we do in the graphical user interface, and we can modify them easily and rerun it so as to automate the mundane tasks. For example, there are a lot of boards which we want to simulate, and then the typical workflow is importing the board CAD, applying the materials, applying the boundary conditions, and then simulating the model and exporting certain temperatures on the board. So this is a typical workflow that I have described. That workflow can be fully automated. So right from importing, applying the material properties, boundary conditions, simulating it, exporting the report, all of this can be automated. Uh, and it saves you a lot of time when it comes to doing those repetitive tasks. By the way, these automation capabilities are not only for Icepak, these are all for all the electronic suites, so we can utilize it effectively even if we are doing HFSS design, Maxwell design, Icepak design, all things available in the electromagnetic suite. So now let me talk about multi-physics simulations. So any device we take, there are like a lot of physics involved. For example, HFSS, Maxwell, Q3D, these are on the electromagnetic side. And so my colleague Nijas talked about HFSS in the prior session. There can be like chip level modeling. We can have a PCB level modeling. And then we want to again see the stresses in the board using mechanical, predict the lifing using Sherlock, or we want to build reduced order models using Twin Builder. So Icepak is well connected with all these different solvers. So that is where it makes it even more beneficial when it comes to solve the real world problems, which are typically multi-physics. So maybe 2, 3 physics are involved, and then we want to exchange information between different tools effectively and then do the simulations. All of this can be easily done using the multi-physics framework in which these tools are sitting. So I'm going to talk about some examples in the coming slides on the multi-physics solutions. So the first is board heating. So we have traces in the board, and then they do carry certain currents, and then because of that, based on the width of the trace and thickness of the trace and the amount of current it passes through it, it is going to heat up. So we need to predict those losses and then transfer those losses to Icepak and predict the temperatures in the system environment. Why do we care about this? Because the devices are getting smaller, we don't have much real estate, and also current densities are getting higher. So as the current densities are getting higher, we are bound to get certain hotspots, and then that we need to mitigate early in the design rather than at the end. So that is where this is the workflow which describes the multiphysics two-way coupled simulation between HFSS 3D layout and Icepak as highlighted here. So basically what we are doing is we are solving for DC currents in HFSS 3D layout, transferring the power map for each plane, for each layer of the board into Icepak, then generating the temperatures, feeding back the temperatures to SI wave to recalculate the losses. And again, this loop iterates. There are certain criteria to exit the loop, but we can effectively do this two-way coupled simulation to accurately predict the port temperatures. Now, just to give an example here, you see for this particular case, if we do not use the heating in the board, heat losses in the board, we are just predicting 40 degrees C as a max temperature. But when we do this coupling analysis between the HFSS 3D layout and Icepak, we see that at the end of the iterations, several iterations, we see the temperatures are as high as 76 centigrade. So this is where this comes in handy to accurately predict the board temperatures in an automated way uh, by bidirectional exchange between the HFSS 3D layout and Icepak. Another example that I want to talk about is reduced order modeling. So why it is important is when it comes to inverters used in the EVs, they are going to have different drive cycles for which we need to do the evaluation and ensure that temperatures are not exceeding the limits in those drive cycles. Now, certainly the doing a 3D CFD simulation for a transient which may last for 30 minutes, 1 hour, 2 hour, it's going to be very costly in terms of simulation. As against that, here is the workflow where we produce the training data in Icepak one time, and then that training data is transferred to Twin Builder or the simpler tool where it generates a reduced order model. So reduced order model can do all these duty cycle evaluations for the inverter in less than a minute. So it doesn't solve the 3D physics, but it does get as accurate results as 3D physics using the reduced order model, using the training data that we have generated one time. So this is the benefit where we can significantly reduce the design cycle for evaluating transient scenarios using the reduced order models. Another multiphysics case that I want to talk about is we can do electromagnetic simulation as showed here at the top, where we are predicting the losses in the board, then transfer the losses in the board to thermal to predict the temperatures, and then take the temperatures to mechanical solver in the same tool to predict the warpage and stresses. So we can do this in a single GUI where we are performing electromagnetic simulation, thermal simulation, and mechanical simulation to get the complete idea about the product performance.